In the computer graphics series, I'm going to teach the transformation matrices involved in rendering 3D objects onto a display. This video will begin with the matrix that transforms an object parameterized by its vertices into an object within a world coordinate system. I'll call this the M matrix, indicating the translation from the object's coordinate system into the world's coordinate system. Many three-dimensional objects can be completely characterized by its vertices. For example, 8 points can completely characterize a cube. In 3D space, these vertices have their position determined by a three-component vector with x, y, and z. When we render the object from the vertices, each vertex is mapped to device pixels, and the z-axis refers to its depth. Then a graphics library like OpenGL, which I'll be using in this video, will build primitive shapes out of groups of vertices passed to it in a buffer. Scaling a three-dimensional object requires a scaling factor be applied to each dimension of the object points. For example, we can double a cube by scaling each vertices by a factor of 2 in all of its components. This example here multiplies the scalar 2 by a three-dimensional vector, and the result you can be seen just scales each component by the scalar. A scaling matrix can also distort the object by scaling the three dimensions differently. For example, a vector of scaling coefficients can be applied for the x, y, and z components, and a matrix-wise a element-wise multiplication can produce a different coefficient for the three components. We can implement this operation as a transformation matrix like this. It resembles an identity matrix with the 3 ones on the diagonal scaled by the x, y, and z scaling factors. A rotation matrix can be neatly expressed as a change of basis matrix where the new basis vectors are at an angle offset from the original ones. So we can write out a vector in terms of the basis, which is the x and y axes. But we could rotate this basis to produce a new basis where the x and y basis vectors are now rotated from their original positions. And then if you take a linear combination of these two new basis vectors using the original point, that has the effect of rotating the point into the new basis. So with this intuition, we can set up a rotation matrix in 2 dimensions by using the new basis vectors as the column vectors of the matrix. Now, in 3 dimensions, one way we can think about this is we could do 3 different rotation matrices in the 3 constant planes, the xz, xy, and yz planes. So I'm showing those matrices here. The y one is just slightly different because it produces a left-handed system, and so you just invert the direction of rotation so that all rotations are counterclockwise. Now, the issue with this is a phenomenon called gimbal lock, where basically you're concatenating 3 rotations, but one after the other. And so if 2 of the planes were to align after several rotations, then you lose a degree of freedom. And so oftentimes the rotation matrix is preferred to be expressed with an axis of rotation, where you're constantly rotating around a single axis. And I'll show that in the next slide and also give a visual demonstration. A rotation matrix that rotates a point P around a given axis can be generated from the axis of rotation, which I'll be showing as bold A, and the angle to rotate. So the matrix is generated by finding a plane of rotation for this axis, which in other words is just the plane that's normal to the axis of rotation. So given a point P, we find the normal plane by taking the cross product of A and P to find the first basis vector, then cross it again with A to find the second basis vector, And note that when you cross it with A again to get that second basis vector, you've produced the additive inverse of the difference vector between the point P and A. So we can represent our resulting equation to get essentially your result vector, which is the change in your position after you've rotated around the axis of rotation A by theta, or by the degree sign as I'm showing the angle. We can represent this equation as the projection of P on A, which is A times A dot P, plus the rotation component in the first basis vector in the plane of rotation, which is sine of your angle times A cross P, and then plus the rotation component in the second basis vector of the plane of rotation, which is P minus the projection of P and A. Now you can sort of FOIL this in some of the terms and collect like terms to yield the following equation. And then finally you can rewrite all of the cross products with a cross product matrix, as in instead of doing the cross of a vector with a vector, you write A in matrix form where the matrix multiplication gives you the cross product. And that yields this equation where a P minus P is added to the 1 minus cos term and FOILed out so that the cross product matrix of a squared can be used. So then the resulting rotation matrix from all of this is as follows. And I'm not really going to go too deep into the math here because I'm going to do a visual demonstration right after this. But I will leave as a final note that quaternions are another interesting way to perform 3D rotations. It just requires a little more background to build the intuition for how a quaternion multiplication can do rotation in 3 dimensions, but there's really great videos on YouTube on that. In my case, all of my graphics demonstrations are going to rely on a single 4x4 matrix transformation, so incorporating a rotation matrix into this is quite good to teach the concept. Okay, so I already have the implementation for the rotation matrix that I just described, where you have an axis and an angle. And this is just pre-computing a lot of the multiplies and then putting them into matrix form. But what I want to show in the code is that I am taking a cross product so that I can render a plane that will help to visualize the plane of rotation. And so your basis B1 is to produce the plane normal to the axis of rotation is A cross P, where my point P is the center of mass of a sphere that I'm going to render and then rotate as I animate the scene. And then B2 is then A cross with B1 again. So we can run this code. As you can see, there is the sphere that's sort of close to this axis, is just below and left of it. The axis of rotation is drawn in purple. The blue line represents the z-axis protruding out of the screen. So I've offset the viewpoint a little bit to the right, and then we're looking at the center of the screen. The y is up and x is horizontal. So you can start animating and unpause the scene. You can see our sphere rotates around the purple axis. It crosses behind when it goes behind it, and you can see the purple rendered in front, and then across. Now, one way to help understand what we're actually doing is to draw the plane of rotation, which I've rendered. And so, with the plane of rotation, you can sort of understand what that math I showed in the last slide was, where we're trying to find a plane to sort of, in the same way that we built those two-dimensional rotation matrices that were in a fixed 2D plane. Now we've found the 2D plane where we want our rotation to occur. And so we make sure that the sphere is rotating around in this two-dimensional plane that is normal to the axis of rotation. A translation in 3 dimensions is really simple. We can just offset each point with a 3D difference vector. So if we want each point to shift right 1, down 1, and back 1, we add the vector 1, minus 1, 1 to each point. To avoid additional operations, we can conjoin this with the entire M matrix by moving to a 4-dimensional 4x4 matrix and converting all points into 4D homogeneous coordinates, where you make your 4th dimension a fixed 1. This way, the 3 offsets stored in the offset vector can be stored in the 4th column of a 4x4 translation matrix, and the matrix multiplication will produce the same translation when we convert back to 3D space. So here is what the T matrix will look like. And as you can, so finally we build the M matrix. I'm showing the scaling and rotation matrices in the homogeneous coordinate space to show how our M matrix can be computed as the multiplication of T, R, and S, and a single 4D matrix can be applied to a buffer of object vertices on the GPU to transform a static 3D shape into the coordinate system of the virtual 3D world you intend to render. So here you see M is T times R times S, or in whichever order you require for your model to world transformation. All right, so let's build the scale and translate matrices. So the scaling matrix is essentially the identity matrix but scaled. And so basically the rows of the scaling matrix are just the scaled. So here it's x, 0, 0, 0. You're just scaling that 1 in the identity matrix by x, and I'm just going to copy this to save time. And as we go down the diagonal, we'll apply the scaling factor to y and to z. And that produces the scaling matrix. And so we keep our 1s in the diagonal, and we apply these parameters as the offsets that will be added in the matrix vector multiplication. Now let's run a program that's going to, here I have sort of brute force the vertices for a cube with every single triangle. There's better ways to do that in OpenGL. And then applying the scaling, rotation, and translation matrix, and I've colored each vertice. So see our cube is rotating around the axis 1, 1, 1. Now, suppose we were to apply the rotation after translation. This is interesting. Now we rotate around the 1, 1, 1 axis, but not starting from the cube coordinates that were centered around the origin. And so the cube is actually rotating around this axis of rotation now.